All right. Hi, everyone. Welcome to a recording of your lesson on exponential equations, right? So today we're going to go over how to solve exponential equations, the difference between linear and exponential functions, as well as exponential growth and decay. All right. So first thing, this one is pretty important because a lot of students get stumped when they see these kind of questions, right? So here are some steps to help you solve exponential equations, all right? So first, you want to find out what the common base is that the numbers can become. Number two, now if they have a common base, great. Use steps 3, 4, and 5 to solve for x or whatever letter they gave, right? The variable. If they don't have a common base, you will need to use logarithms. And we're not going to do any logarithms in this lesson. You'll see equations that don't have a common base, and you need to use a logarithm in another lesson. All right. Now, let's say you do have a common base, right? Once you change those numbers to a common base, you want to apply the exponent rules to simplify the exponents. And we'll obviously see how we're going to do that in a second, all right? And then your fourth set is once you have simplified all the exponents and you have a common base, you can set up an equation using the exponents, all right? That one is a pretty important, the exponent rules, which you should have learned earlier in the weeks, as that always pretty much comes out. So by now, you should be familiar with what the exponent rules are, all right? And how to use them. And then once you have an equation using the exponents, you solve for x or whatever the solution is. All right. So let's take a look at this. We're going to apply the rules. So first things first, I want to look at these numbers, 25 and 1/5. And then I need to decide, okay, do they have a common base? Right? And they do. Like 25 is 5 square. And then I'm going to put its exponent x minus 7 in the parentheses. All right. And then 1/5, its common base is 5 to the power of -1. So as you can see, the common base for these two numbers, 25 and 1/5, is 5. 25 is just 5 squared, and 1/5 is 5 to the power of -1. And don't forget, we need to put 2x over here. Okay, now the next thing we need to do, as you saw in the steps earlier, right, is when you have a common base, apply the exponent rules. Now, as you can see here, because you have a term and it's being powered further, that means you are going to, sorry, not add, you're going to multiply the exponents, right? So you have 5, so nothing happens to the bases, you're only doing this to the exponents, right? So you have 2 times x and 2 times -7, which gives you 2x minus 14 equals 5. And then same thing, -1 times -1 times 2x gives you -2x. Great. And then or off to the fourth set. Now that you have exponents simplify and you have a common base, set up an equation using exponents. As you can see, common base, we can take the exponents and set up an equation, right? So we have 2x minus 14 equals -2x. And then from here, you solve for your variable. So in this case, x. Let's see, I'm going to subtract 2x from both sides of the equation. And that will give me -4x equals -14. Divide by -4, x equals 7/2. And that's my answer. All right. Now we see another question, same concept. Now for this next one, as you can see, we have a radical, right? And if you remember before, we can also change radicals into having rational exponents, right? So a fraction for your exponent. Now remember, the root here is going to be the denominator. So you have 2 1/3, right? And then that way you can compare. Okay, so this is 2. Does 4 and 2 have a common base? Yes, because 4 can become 2 square, as you can see. And then I always say big tip is to put a parentheses around these, right? Because they technically go together, and you are going to be foiling 2 with x and -1. So with that in mind, we foil that. So we have 2x minus 2 there. Okay, same basis. We can make an exponent out of the exponents now. So we have 1/3 equals 2x minus 2. I'm going to write over here. We then have 2x equals 7 over 3 because I added 2 to both sides of the equation. And then from here, I divide by 2 to finally give me x equals 7 over 6. And that's the answer. All right. Next one, okay, 64 to the power of x squared equals 32 to the power of x plus 10. So what you want to do for these questions, right, this one is not as straightforward as the ones before. So this one really does take, some recognizing as well as testing out of what their common base is, right? So the nice thing about the SAT is that you don't have any logarithms on the test. So you know that these equations do have a common base. Whereas for the ACT, they do ask you logarithms, but they don't ask you where like you don't have a common base, essentially. Very rarely they do. So SAT students, you know that this will have a common base. ACT students, you need to figure out, right? But this really just takes practice. So if you notice 64 and 32, they probably do have a common base. Don't try testing big numbers like, oh, 7 square, 7 cube, or 8 square, or 8 cube. They're a little bit too big, right? So try smaller numbers. Like 64, right, is actually 2 to the 6. Right? And 32 is actually 2 to the 5th. So as you can see, the base is actually pretty small. It's just a base of 2, right? And then from here, as usual, we're going to apply the exponent rules. So because it's being powered further, we multiply the exponents. So we have 2 to the power of 6x squared equals 2 to the power of 5x plus 50. Now I can form an equation using the exponents. 6x squared equals 5x plus 50. Now notice, actually, we have a quadratic this time. So that means we need to group everything to one side of the equation. So as you can see, that means I have subtracted 5x and 50 from both sides of the equation to give me this now. From here, I want to factor it. So use whichever method you are most comfortable and familiar with to factor, right? You should get the factors. 3x minus 10 times 2x plus 5 equals 0. From here, solve for x. So split it into two equations. Yeah, and then solve for x. So we have 3x equals 10, x equals 10 over 3, 2x equals negative 5, x equals negative 5 over 2. Therefore, we have two solutions for this question. We have x equals 10 over 3. Oh, let me write all of that nicely. Yeah, x equals 10 over 3 and negative 5 over 2. So we have two answers. All right. So that's how you solve exponential equations. Now on to essentially being able to differentiate the difference between linear and exponential functions. And it goes hand in hand essentially with exponential growth and decay, right? You'll see common questions where they give you a statement and they ask you, is it linear increase, linear decrease, exponential growth, or exponential decay, which we'll actually also see in a second later. But first, here's how you can tell if it's exponential growth if it's linear or exponential in just general, right? So if you notice, linear here are straight lines, whereas exponential is like curved, right? So with linear, if you were also given an equation, right, or maybe even a table, linear is a plus or minus difference. I repeat, it's a plus or minus difference, okay? That's why you have slopes. The slopes are plus or minus, okay? Whereas with exponential growth, it's a times or divide difference. More specifically, the word is ratio, right? It's times or divide. So it might be like, oh, 3 times 2 to the power of x, right? Or 3 times 1/2 to the power of x. But as you can see, it's times, right? If it's 2, and then technically it's divide if it's half, right? In short, for your ratios, this is also another thing you want to look at, which you will see also as we go through questions together. If your ratio is greater than 1, it's showing growth. If your ratio is less than 1, it is decay. All right. So this one also takes a lot of practice, getting used to seeing, okay, how much is the growth? How much is the decay? Is this growth or is this decay and whatnot? And it also takes practice being able to differentiate, given a graph, a table, or a statement, if it's linear or exponential. All right. Now, as you can see, we have some statements here. So examples of questions, including these, they ask interest rates, growth of bacteria, or decay of a radioactive isotope. That's for exponential growth and decay. All right. Another popular question also is population. All right. But here's a little gist of linear and exponential, right? So linear, it doesn't actually have to be linear growth. It's just any linear, right? Straight line. You're generally given in the equation of y equals mx plus b, right? If that rings a bell, because that is the equation of a straight line, the slope-intercept form specifically, right? Where b is the starting amount, aka the y-intercept, and m is the amount added or subtracted. See that? Added or subtracted. So the difference is plus or minus, as I said earlier here, right? Each time x is increased by 1, all right? So linear, most important, it's a plus or minus difference, okay? Now exponentials, it's a little funky depending on the situation. Generally, with interest rates or interest questions, you use this with, more specifically, actually, it's A equals P times 1 plus R over N to the power of NT, but that's specifically for interest. For like bacteria, decay rate, population, it's this as well as this, depending on the situation, right? But as you can see, A here is the y-intercept or the initial amount, right? And B is the amount that it's multiplied or technically divided, depending on what the ratio is. Again, more than 1, it's technically multiplying, getting bigger. If it's less than 1, that B, it is decaying, it getting smaller, generally as a fraction if they show it, right? Maybe they give it a decimal, so that's how you also differentiate it if it's increasing or decreasing. All right, each time x increases by 1. Now, as you also notice with exponential equations, right, your x is going to be the exponent, all right? Because what we have seen over the years is that students get confused between exponential equations and quadratic equation. So this is a quadratic equation. As you can see, our x is a variable and our highest degree is 2. It's different from exponential equations because the x is the exponent. So that's also another way you can tell a difference actually between quadratics, highest power is 2, and your x is a variable, compared to exponential equations where x is the exponent, all right? So you want to take note of that. X is the exponent in exponential equations, all right? And yeah, exponential growth and decay, you also use this. R is your rate, so if it's growing, you add the rate. If it's decaying, you subtract the rate because it's supposed to get smaller, right? We'll see in a second with oh, actually not in this case, but just one thing you want to take note of, if it's decaying, right? So normally your rate, for example, A equals for maybe 0.96 to the power of T, maybe it's bacteria population. This tells me how much of the initial population is going to remain after T hours per se, right? For example, that means my decay rate is 4% because I lost 4% of my population after an hour, which means 96% of my population remains after an hour. So this here, that's why with decay, you have to be a little bit more careful when you read it or when you put it into the equation, right? This tells you how much remains after T amount of time or X amount of time, all right? Now let's look at some questions. 4 years ago, Jason earned $3,000 doing private catering jobs. Every year since then, he's doubled his catering income. Which of the following types of functions best describes the yearly change in Jason's income, right? And as you can see, you're trying to determine if it's linear increase, linear decrease, exponential growth, exponential decay. You want to look for the keyword here, right? Whether it's telling you it's adding, it's subtracting, it's multiplying, it's dividing, right? Your keyword here is double. What does double signify? Times two, but times, right? Because it's telling you times two is going to get even more and more and more. So that tells me it's an exponential decay. All right. Linear increase is a plus difference. Linear decrease is a minus difference. Exponential growth, as we have just seen, is a times difference of at least, greater than one. And an exponential decay, right, is a divide. Or in other ways they could word it, right, is they times by a fraction that's less than one. All right. So this is how you can tell. Exponential decay again, be careful. Now let's look at this. Now we're given a table, right? The table below shows 4 values of f of x. Which of the following best describes the function? Okay, so again, we're trying to determine if it's linear increase, decrease, exponential growth, exponential decay. So first thing you want to notice, okay, x are all increasing by 1, and that's fine, right? We just need to know what the interval is for your x. Right? Because if you remember also from this definition here, right? Each time x increases by 1. All right? So now we are actually mostly looking at your f of x or your y in this case, right? We want to notice what the pattern is. Is it plus or minus? Is it times or divide? Now, what I could do, right, is I can try, 21 minus 7, that is going to give me 14. Okay, and then if I do 63 minus 21, right? Because if you're going to try to find a pattern, you always want to do number after divide by number immediately before, right? So like in this case, 21 minus 7, 63 minus 21. Same thing also when you're finding the ratio, 21 divided by 7, 63 divided by 21, right? To find out what it is. Now, from here, as we can see, right? This is a difference of 42. So it's not the same difference. So we know it's not linear, nor it's not linear at all, right? So now it's between exponential growth and exponential decay. So here's how we can tell if it's growth or decay. Again, growth is when the ratio is greater than 1. And decay is when the ratio is less than 1. So how do we find the ratio? Again, after divided by immediately before. Okay, this is 3. Then we check again to see 63 divided by 21. Okay, still ratio 3. And then we even do 189 divided by 63. Because remember, after divide immediately before to find the ratio, you get 3. Since all of your ratios here are greater than 1, it is an exponential growth. All right. And this is how you can tell if it's linear or exponential if you're given a table. All right. Now that's it for today. If you guys have any questions, send me a message or an email. I will see y'all soon. Bye.